Assalamualaikum. Good morning. Can you hear me?
Yes,
Salam, can hear Doctor.
Okay. So welcome back to the second half of the semester. Selamat Hari Raya Aidilfitri, maaf zahir batin. For today class, we make it online first because the classroom seems not ready yet. So inshallah on Wednesday we will apply face-to-face inshallah on the Wednesday 12 p.m. So we go to the 2.6 chapter 2b. Hello? Okay. Chapter 2b, which is a tuning of PID controller using the second method, namely known as Cohen-Kuhn tuning method. So last 2 weeks, I discussed with you the first method, which is the Ziegler tuning method. Okay, so this is the first one. So the second one is the Cohen-Kuhn tuning method. So this method works well on process where the date time is less than 2 times of the time constant. So date time is known as time delay. Okay, the symbol is TD. So what actually is time delay? Time delay is from the time response. If you have a time response, a closed loop time response, for example, okay, this is time response. This is the output, and this is the input. Okay, so the time, the output is something like this. Okay, so this is the output, and let's say this is 1 second. So time delay is the time taken for the response to start a transient. Okay, to start a transient, go to the peak and then oscillate and then settle at the final value. Okay, so this period between 0 and transient response pickup be known as a time delay. So in this case, time delay is equal to 1 second. And in the expression of the time response, it will be like this, minus t. Okay, exponent minus t. So 1 second is 1 multiplied by t lah. So exponent minus t. Okay, so in this case, time delay is less than 2 times of the time constant. Okay, so meaning that TD is less than 2 TC. So TC is a 63% of the output of the final value where the time occurred. So which is the time constant. Okay, so suitable use for self-regulating process based on characterizations of process by a simple first order steady state gain, K, time constant, and date time. Okay, let's say we have a time response, first order. Okay, so this is the input, usually 1 volt, and the output, okay, first order, okay, something like this. Okay, so that is the first order. Okay, so time constant is roughly, is about here, 0.63. So this is the time constant. So in order to do Cohen-Kuhn tuning method, so a step response of the open loop system has to be obtained. Okay, step response of the open loop system has to be obtained. The response is known as process reaction curve. Okay, we call it as process reaction curve. And the reaction curve must cover the entire test period from the introductions of the step test until the system reach a new steady state. Okay, so typically this will take a few minutes or several hours depending upon the speed of the process. So usually we have a dynamic process and static process. Okay, so dynamic process usually involving motor, generator, okay, which turn quickly, compared to static process which involve a tank, okay, 2 tank, couple tank, triple tank, okay, which involve a process control system. So once the step procedure is carried out, the process reaction curve is matched to a simple process model. Okay, process reaction curve will be matched. Okay, will be compared to a simple process model in order to determine the model parameters, which is known as the gain K, time constant TC, and time delay TD. Okay, K is the gain, time constant is the TC, which is 63% of the final value, and the date time. Okay, the period start from 0 to transient response. So this is can be right in the yellow equation, which is known as the first order process with date time, okay, or time delay, okay, which is GS is equal to K exponent minus tau A or alpha, tau alpha S, okay, divided by tau S plus 1. Okay, so K is the gain. Okay, minus T alpha. See, T alpha is the time delay. And tau is the time constant. So thus for the step change in the controller output, okay, of the magnitude delta M, let's say the magnitude is delta M, we have a equation, first order process with date time, okay, multiplied with the delta M divided by S, where CS is the output of the process, okay. So this one, it looks like an input lah, okay, step input that we inject to the system, okay, like this, okay, step input. So the value of DC is given as shown in the figure below, which shows a typical process reaction curve. So this is the magnitude, delta M. It can be 1 volt, it can be 5 volts, depend on the signal that we inject. And this is the response, okay. You can see that there is a time delay here at the bottom of the response. So the step response below illustrates how the gain K, the time constant TC, and the date time TO are estimated using a first order process with date time fit method. It's actually like a curve fitting lah. It's curve fitting. We try to fit this equation with the input step, okay, as shown here. So it's more towards curve fitting. So in general, we have a model, okay, the mathematical model, which is fixed, and then this actual is the real experiment. data from the real experiment. Then we compare with the mathematical model, and it looks that the model and the actual fit very well together. Okay. So to estimate the time constant and the time delay, we can use one of the fit method proposed. This method uses the line that is tangent to the process reaction curve at the point of maximum rate of change. Okay. So for first order process with time delay model, this happens at the T naught, okay, which is plus tau K delta M 1 minus exponent minus 1, which is more or less about 0.632 delta CS. Okay. So the value of TC is the one that forced the model response to coincide with the actual response at time is equal T naught plus tau. So this is one of the example of finding a time delay and time constant. Okay. So for your information, time delay is dead time. Okay. So we use the terms time delay is more appropriate because dead time quite scary among students. Okay, dead time. So we just replace it with the time delay. So the tangent line is here, which is to the maximum of the PV slope. Okay. And then we measure the 0.66 of total PV change. And then we will get the time delay and the time constant. Okay. So the time delay is beside the time constant tau. And for the tuning, okay, so we still need a table, okay, similar to the Ziegler-Nichols. So if the controller is P, we use this table. PI, we use this table, and PID, use this standard table, okay. And the actual PID transfer functions is KC 1 plus 1 over TIS plus TDS. Example. So the input shown as R of T, okay, this one, the blue one, and Y of T is the red one. Tune the PID controller. Okay, so we calculate the K, which is delta CS divided by delta M. Okay, so delta CS is about here 0 to 0.6. Okay, so 0.6 delta CS, and delta M is start from the blue 0.2 until 0.7. Okay, so we get 0.5. Okay, so this one is 0.6 minus 0.0. This one is 0.7 minus 0.2. So we get K 1.2, and TD, the time delay is 1 second, okay, which is over here. Okay, time delay is 1 second. Time constant is 1.8 second, which is 63% of the final value. So you insert the TD and tau together, okay, TD plus tau, which is 0.632 delta CS. So we'll give you 0.32, okay. And from there, you calculate the KP using the table, okay, TI and TD, okay. So just pick up from here, just pick up from here, just pick up from here. Then you will get 1.8, 0.9, and 1.8, and replace it into the GPID. So you will get the final value of 1.8 plus 0.9 divided by S and 1.8S, where Kp is 1.8, Ki 0.9, and Kd 1.8. Okay. So alhamdulillah, we finish proportional controller, PI controller, PD controller, PID controller, and tuning of PID, which is Ziegler-Nickel and Cohen-Cook method. Okay, there are so many methods of PID tuning. If you go to Google Chrome, okay, there's a lot of methods. So we can Google if you want. Okay, let's say you go to the Google Chrome. Okay, PID tuning method. Okay, so let me go to settings. Okay. Okay. Tuning method. Okay, so we have a see what the method you have. Okay, so we have a lot of method actually. Okay, to tuning it. Okay, actually we this tuning method is actually we want to control the valve. Okay, the valve of the process. Okay, you can read by yourself. Okay, a lot of method there, and some videos on the PID control tuning method. Okay, so we just focus on two methods only for these subjects. Any questions? Any question, guys?
No, Doctor.
Okay. If no question, we move to chapter 3. Okay, so chapter 3 is a frequency response and stability analysis in frequency domain. So what is the content of the lecture? First is to introduce the concept of frequency response. Okay. Then a simple open loop Bode plot. Then Bode plot for overall plotting. Analysis Bode plot using a Nichols chart and MATLAB simulations using a MATLAB software. Okay. So the concept is in time domain, we use step signals, impulse signals, and parabolic signals, and RAM signals. But for frequency response, we're using a sinusoidal. Okay, sine wave to a linear system to generate sinusoidal of the same frequencies. However, when you inject the sine wave into the process, okay, they will differ in terms of amplitude and phase angle. Okay, amplitude and phase. Okay, so this can be represented by this equation, m1 cos omega t plus sine 1, which is equal to magnitude and phase. So this is the magnitude or amplitude, and this is the phase. Okay. So thus the system can also be represented by a complex number, so that the product of the input phasor and the system yield the same phasor of the output. So this is the concept. So this is a sine wave. Okay. So you inject inside the input. Okay. And you get the output. Okay. So the output will be this one. Okay. So it will differ. The amplitude differ and the phase also differ. Okay. And this is the mathematical model, okay, that we observe from the output and the input. It seems that the output sinusoid is found by multiplying the mathematical model and the input. So this one can be first order, second order, okay, third order, and so on. Okay. Okay, Shahir Ridwan. Shahir Ridwan.
Yes, saya, Doktor.
What is the definition of first order system? Tak dapat. Lama nak raya. Daniel Zulkifli. Also cannot answer. Farhan. What is the definition of first order system? Tak datang. Yuki Wong.
Yes, Doctor.
What is the definition of first order system?
Only got one
The system that has one
host.
What? One host,
One zero post.
one pole, single pole. Can you repeat again?
The system that has one single pole.
Liana Camelia.
Yes, Prof.
What is the definition of second order system?
System that has two poles.
Two poles. Ni Muhammad. Ni.
Hello, ya, Prof.
Selamat Raya.
Selamat Raya.
What is the definition of third order system?
System that has three poles atau denominator dia S cube, betul?
S cubic.
S cubic.
S cubic. So from the equations, okay, that we multiplied between the input and the mathematical model. So this is the equation, and from there we can simplify the magnitude of the frequency response, which is the output divided by input. Okay, So we get magnitude. And phase frequency, so since it is output and input, so the output will minus the input for the phase frequency response. The combinations between the magnitude and phase is known as the frequency response. So this is the magnitude and this is the phase. So the frequency response of a system with the transfer function of Gs is known as Gj omega equal to Gs, where S is equal to J omega. For example, if you have a transfer functions of 1 over S plus 2, first order system, okay? So first order system, pole at -2, no zeros, okay? So we can find the magnitude, which is this one, okay? 1 over square root omega square divided by 4, okay? So omega ni is a frequency value lah, okay? And for the phase is, since it was a denominator, so it is minus inverse tangent omega divided by 2, okay? So one way to plot the frequency response is by using a separate magnitude and phase plot, okay? So we call it as the magnitude, the ratio between the output divided by input, and then we get 20 log, okay? So that it will give you the decibel value, okay? Log scale lah, eh? And then the phase curve is phase angle versus log frequency, log omega, okay? So we know give as a boat plot macam ini, okay? So this is the boat plot. This one is the magnitude plot. This is in decibels, and this one is the phase plot, which is in degree. Okay. So we can see that the frequency value, which is a radian per second, is in log scale, 0.1, 1, 10, and 100. So this is known as 1 decade, 1 decade, and 1 decade. So this graph have 3 decades. 1 decade is equal to the 10 frequency values. So what is the values of here? 1 Muhammad Alimi. What is the value over here?
0.2.
0.2. Faris Haikal,
Yeah,
what is the value of here, frequency?
1.2.
1.2. 1.2. Decade. Astaghfirullah. Al-Azim. Alah tu. 1, 2, 3, 3
Oh, 1.2.
radian per second. Astaghfirullah. Al-Azim. Banyak sangat makanan ketupat. Ahmad Najwan. Ahmad Najwan.
Yes, I am here, Doctor.
Selamat Hari Raya.
Selamat Hari Raya, Doctor.
What is the value of this frequency value?
Ya. Mana, Doctor?
Niha. Kau kat mana? Kau pakai telefon eh?
Tak. Pakai laptop.
Ha. 10. Lepas 10 apa? 11. Astaghfirullahalazim. Si Micin. Si Micin.
Hai, Doctor.
Hai, selamat Hari Raya. What is the value of frequency here?
Mana?
Sini.
Oh, ini. 40.
40 ah.
Hmm.
So 10, 20, 30. Okay. Aduh. Sabar. Okay. So another way to plot a frequency response is by using a Nichols chart. Okay, so this is alternative way. But in this subject, we are being instructed not to teach Nichols chart. Okay, just to inform you that there is another way to plot a frequency response. So the log magnitude and phase frequency response curve as a function of log omega is called a Bode plot. Okay, so it's a technique for analyze and design of a control system. So consider transfer functions here, ds, and the magnitude frequency response, which is gj omega. Okay, then we convert into the decibel. Okay, we get a 20 log gj omega, and the phase frequency, which is a magnitude and the phase. So if we know the magnitude and the phase response of each term, so the total frequency response can be obtained by using algebraic sum of each term. This frequency response can be simplified by utilizing a straight line approximations. So meaning that we have two ways. One is using straight line approximation. The second one is using a real point. This is by computer. Okay. Of course, when you apply both straight line approximations and real points by computer, there is a small error that is acceptable. Okay, but the shape is there. Okay. So Bode plot factor. Okay, I forgot to tell you how to draw the Bode plot using a MATLAB. Okay, shall I show you here? First, we open the MATLAB first. But before we go there, I shall to inform you that for this plot, okay, so the transfer function is gs 1 over s plus 2. Is the first order, okay, first order system, single pole, okay, and the break frequency is at 2 radian per second. So this is 1 and this is 2. Okay. So the blue one is by real point. But the straight line approximation is something like this. 20. 20 plus 6, 26. And then here. Okay. Then it goes down like this. So the red one, we call it as a straight line approximation. Okay. Okay, MATLAB is come out. So we just go to the MATLAB. Can you see my MATLAB? Guys? Can you see my MATLAB?
Yes, Doctor.
Yes, doctor.
Can, Doctor.
Ashraf? Ashraf,
Yes, Doctor.
the transfer function?
1 over s plus 2.
Okay, thank you. So G is equal to 1 over S plus 2. Okay. Then the command is both G. That's all. Okay, both G. Okay, so I share the figure. Can you see? Can you see the figure?
Yes, Prof.
Yes.
Great. Okay. Okay. It's about the same lah. It's about the same. I share in the WhatsApp. Okay, 1 over S plus 2. Then you still can scan the value of the magnitude at the 2 radian per second. Okay. Chong Juan. I have one question. The break frequency is at 2 radian per second. What is the value of the magnitude at 2 radian per second? How to find it? Magnitude at 2 radian per second.
Find a point on the graph.
Scan lah. Scan.
Mm.
Scan lah. Scan lah. The keyword is scan. Minus 2. Belum lagi mah. 2.56.
Ya, belum.
Berapa?
9.02, negative 9.02.
Negative 9.02 decibel. Okay. Nur Atika. Nur Atika,
Yes, Doctor.
what is the value of phase at 2 radian per second?
Okay.
How to find it?
Scan.
Scan.
Use the same method.
Yeah, okay. Scan. Okay. What is the value of phase at 2 radian per second?
Negative 45 degree.
Negative 45 degree. Bagus. Okay. So I share with you again. The value of the magnitude and the phase at corner frequency or break frequency. Okay. Okay guys, boleh? Can So corner frequency is equal to break frequency. Same. Okay, some book using corner, some book using break frequency. So we're going to see the both plot factor for constant K, zeros at the origin, poles at the origin, zeros at real axis, and poles at the real axis. Okay. So this is the zeros, which is here. And just now, we discussed on the poles at the real axis. For example, we have a constant K. Okay, this is the way we find the magnitude and the phase for constant K. Okay, and we show you the magnitude versus log frequency and plot phase versus log frequency. So dia adalah constant lah. Okay, constant, you know. So we go to the MATLAB, choose one value of constant. Con Yawen. Con Yawen.
Yes, Doctor.
Choose one value of constant. K equal to what? What number you like?
7.
Oh, you like number 7, huh? K is equal to 7. So, both K. Okay. Oh, tak boleh, eh? Oh, okay. I understand. G is equal to 7. Okay. So, both G. Oh, also cannot. So, constant is like this. Okay. Let's say K is equal to 7. 20 log 7 berapa? Con? 20 log 7.
16.902.
How much? Twenty multiplied by log 7. 16.9 decibel mah. So dia punya frequency response dia is straight 16.9 decibel. Okay. And the phase is 0. Okay. (0°). Okay. So that is the frequency response for constant K equal to 7. But for zeros as the origin, so this is the zeros at the origin. GS is equal to S. Okay, you can see that when we plot, we get a slope. Okay, the slope here is positive 20 decibel per decade, and the phase is 90 degrees for zeros at the origin. Okay, zeros at the origin, macam ni ya. Okay. Poles at the origin.
Doctor, you're not sharing your slide.
Sorry, Kak. Okay. So I repeat again. Okay, so this is the gain at 7. K equal to 7, 20 log 7, 16.9. So this is the magnitude response for constant 7, and phase plot for constant 7, which is at 0 degrees. For the zeros at the origin, okay, so it will give you a straight line with the slope of 20 decibel per decade, positive. And then the phase is 90 degrees. And for 1 over S, which is poles at the origin, okay, so it will give you a straight line with the slope of minus 20 decibel per decade. Okay, minus 20 decibel per decade, and the phase is minus 90 degrees, straight line, horizontal line. Okay, we have a break for 10 minutes. Okay. Is it okay? Have a break for 10 minutes. Guys, 10 minutes break. Hello.
Okay, Doktor.
10 minutes break. 10 minutes break.
Okey doktor, boleh doktor.
Okay, guys, we continue the second hour of the class by referring to slide number 15. Okay, so if we have zeros at the real axis, okay, that is the zeros at the real axis, and the transfer function is s plus a, okay, s over a plus 1. Find the magnitude omega over a square, okay, plus 1, and inverse tangent omega over a is the phase formula. Okay, so to plot the book plot, we have to apply 3 assumptions. Can you hear me? Dengar tak? Hello?
Dengar doktor.
Can
Okay.
doktor.
So 3 assumptions, which is omega very small to a, omega equal to a, and omega is greater than a. Okay, so when omega is less than a, 0 degrees, then omega equal to a, 45 degrees, and when omega equal to the value of the greater than a, which is 90 degrees. So this is the high frequency approximation. We call it as a high frequency asymptote. And at 45 degrees is we call it as a break frequency or corner frequency, because the response start to change from 0 to a value of the magnitude. Okay, so this one, the lower one, we call it as a low frequency asymptote. So between low frequency asymptote and high frequency asymptote, we have a corner frequency. Okay. So as I told you before, for zeros, we plot using 2 methods. Okay. First method is using a real point. So real point is by computer. Okay. So insert the transfer function value, and then we call a board G, and then it will plot real point. The second one is using straight line approximations. So here you are. The real one is called actual, and the estimated one, we call it as asymptotic approximations. You can see there is some error here, okay, but the error is very small and reasonable and accepted. So in this case, the corner frequency is 1 radian per second. Okay. There you are, the high frequency asymptote, the low frequency asymptote, and in between will give you a break frequency. Similarly to the phase plot, okay. So this is the phase plot versus log frequency. So you have 2 plot here. One is the actual by computer generations, and the other one is by asymptotic approximation. Oh, kita panggil as a penghampiran garis lurus. So same again between the high frequency asymptote and low frequency asymptote. So we have asymptotic approximations. So come back to the fifth one, which is pulse at the origin. Okay, let's say we have a pulse at the origin. We find the magnitude, which is here, 1 over square root omega divided by a square plus 1. And the phase is minus arctangent omega divided by a. So we have omega less than A and omega equal to A plus omega greater than A. So at omega less than A is 0 degrees, and omega greater than A is minus 90 degrees, and in between there is a corner frequency which will produce minus 45 degrees with a slope of minus 20 dB per decade. So this is for poles at the origin. So A is the corner frequency, okay? And the corner frequency will give you minus 45 degrees in between high frequency asymptote and low frequency asymptote. All right, so example 1. So sketch the ball plot for the open loop system shown here for K S plus 3 and S plus 1, S plus 2. Okay, so what should we do now? Okay, so this one, if you want to plot by computer, you just key in this one. Okay, then you get the ball plot. Or if you want to use a straight line approximation, of course, you have to normalize first. Okay. 1 and 2. S plus 1, S plus 2. Okay. So this will give you 1.5K. S divided by 3 plus 1. So S plus 1 plus 1. S over 2 plus 1. Okay. And use the command MATLAB to get the actual both G. So in test 2 and in final exam, you are not required to draw MATLAB, but you have to sketch, freehand draw for this particular transfer functions. Okay, so how to use a straight line approximation? We have to draw. Okay, we have to draw. So the GS is 1.5K. S plus 3 plus 1. Okay. Okay. So first you draw the magnitude. Okay, sketch. Okay, freehand draw. So we start with the 1.5K. So we assume K equal to 1. Okay, assume K equal to 1. So 20 log 1.5. Berapa? Si Micin? 20 log 1.5.
3.52.
3.52 eh? Okay, sini lah Decibel eh? And then S plus 3 plus 1 is here. Just goes here. Then it goes down. 3 radian per second. Okay. Sorry. Naik atas. Up 3 radian per second. Okay, slope is positive. Then S plus 1. Okay, kat sini. So your slope is like that. 20 dB per decade. Then S plus 1 plus 1. It's another one. Okay, go down. Okay. And then S plus 2, another one, and go down. Okay. So this is 2, and this is 1. That is for the magnitude. And then you do for the phase as well. Okay, so for the phase, Constant is 0 degrees. Let's say 0 degrees over here. Okay. And then this one is S plus 3 plus 1. So 3 radian per second. Okay. 0. Okay. Okay. So this one is 0.3. This one is 3. So this one is 45 degrees. Okay, sketch by hand. So previous test questions and final exam, they ask you to do the freehand draw. Okay, sketch. And then for this part, S, okay, the face is 90 degrees. So 90 degrees, you just take the blue one. Okay, just draw like this. So that is a 90 degrees. Then for this one, S plus 1 is minus 45. So let's say this is minus 45. This is 90 degrees. So it happens at 1. Okay. So it is like this, goes down, go down. Okay. So that is for 1. And second one is S plus 2. So 2 is here. So it goes to the green one. Okay. Goes down. Goes down. Okay. So that is for the second one, this one. Okay. Or you just go to the MATLAB. Amir Zafran. Amir Zafran. Amir Zafran, are you there? Patrick Ko, can you read for me the transfer functions? Patrick Ko, tak datang. Ivan, can you read for me the transfer functions? Ivan Tan, tak datang. Sharizal, Sharizal, tak datang. Wenjin, Wenjin, can you read for me the transfer functions?
Bracket S plus 3 divided by S.
Okay, K is 1. So K is 1 multiplied by S plus 3.
S plus 3. Then divide
by
S.
S multiplied
S plus
S
1. And multiply S
multiply.
plus 2.
Okay. So both G. Okay. So you get the so this is the plot or the can you see the plot? Okay. Zaris Aiman. Zaris Aiman.
Yes,
Ah,
doctor.
what is the value of magnitude at 0.01 radian per second? How
43.5
Radian
per second.
per second. Ahmad Faleh? Ahmad Faleh? What is the value of the phase at 1 radian per second?
$143
Minus 100.
minus 143.
All right. So that is the plot using and the code is here. Okay. Then you get this plot. Okay. Share the same thing that I got just now. And this is the one that I sketched. So at the end of the day, you have to add so that you find the total of the boat plot. So boat plot for the second order. So for the second order, we have a standard model structure, which is omega n square over s square plus 2 zeta omega n s plus omega n square. Omega is the undamped natural frequency. Zeta is the damping ratio. Okay, so don't get confused with omega d. What is omega d? Natrah, Hassan. Natrah?
Ya, Doctor.
Omega y.
Yeah, magic frequency.
Omega y, Natrah.
Ya, Doctor.
What is omega d?
Jadi,
Hmm.
yang natural frequency.
Omega n is undamped natural frequency. Zeta is damping ratio. What is omega d?
I forgot it.
Huh? You forgot it. You forgot. Safwana, tolong Natrah.
Is
Safwana.
it over them?
Huh? What is omega d?
Them natural frequency.
Damped natural frequency. So please take note. Okay. Please take note, guys. So if you have a root locus, ni kan? So you have a macam ini. So you have a macam ini kan, root locus kan? So this one is J omega D. Okay, or sama dengan J omega n 1 minus theta square. So this value is omega D. Guys, clear? Damped natural frequency. So yang undamped tu macam mana? Yang undamped tu is the beam tu, grid dia tu. This one is dia punya omega n. Okay. Si Michin,
Yes, doctor.
what is the difference between omega n and omega D?
One is undamped, one is damped. No?
Okay. Okay. So one is undamped, one is damped lah. Is a apa? Is a twin lah. twin but not the same. Omega n and omega d. So in second order system, we have this is the model structure, and then we normalize, and then we differentiate between the imaginary part and the the real part. Then we apply the low frequency and high frequency, omega smaller than omega n, omega greater than omega n. Then we plot. So the corner frequency here is the omega n. But the slope, okay, the slope tu berapa? Berapa? What is the slope of these straight line equations? What is the slope? Chua Leon?
Yes, doctor. Yes, doctor.
What is the slope of this line? Shh.
Not sure.
Huh? Not sure. Slope. Tak tahu. So kita tanya Natra Hassan. Slope dia berapa? Natra? Natra?
Higher the slope.
Kecerunan. Apa
Oh.
dia? Ya. Ah.
One. Negatif 4 tu.
Negatif 40 dB per decade. Sini kan negatif 40 kan? Sini kan 1 kan? 1 decade. So bagi negatif 40 dB per decade. Miss Chua? Miss Chua? Okay tak?
Yes, doctor. Yes, doctor.
Faham?
Yeah,
Faham,
faham. Yeah.
Off mic.
Thank you.
Bising. Right, so this one also the same for the phase plot. So this is the corner frequency, and this is the low frequency asymptote, and this is the high frequency asymptote. And what is the slope for this line? Atika? Slope dia berapa? Menurut Atika? Tidur? Tak. Ada. Ada eh?
Negative,
Tidur.
negative 90.
Negative 90 degree per decade lah. Ini 1 decade. Ini adalah minus 90. dy dx okay. Astaghfirullahalazim. Okay, so this is the GS normalized, and at the break frequency we get minus 90 degrees. Okay. Okay guys, so for second order system, complex conjugate poles, CCP. Okay, so we have a standard graph which vary from 0.1 until 1.5, the zeta value, and which will give you a different amplitude at corner frequency. Okay, so the highest one is 0.1, 0.2, 0.3 until 1.5. Okay, so this standard graph will be attached if you want to make an approximation of the zeta value. For example, okay, for example, if your response is something like this, okay, So what is the estimation zeta value for the red line? Leong Kahau. If you have a magnitude response of the red line, what is the estimation zeta value? Tak datang. Jason Lau. Tak datang. Ramai tak datang. Safwana, what is the estimation zeta value for the red line?
Between 0.1 and 0.2.
0.1 and 0.2. 0.15 lah. So that's why you estimate zeta 0.15. Can I do that? Yes, you can. Similar to the phase as well. For 0.1 and 1.5, it varies. Okay, it depends on the zeta value in the standard curve graph. So you are given this one. Okay. Sketch the workload for GS for unity feedback system shown here. Okay. S+3 over S+2. So you have open loop zeros -3, open loop poles -2, open loop complex conjugate poles berapa? Natra? Natra?
-1 plus 4.8.
Okay. Plus minus J 4.8 Betul? Betul?
Yes.
Right. So dia kata lukis pakai MATLAB. Okay. Lukis pakai MATLAB. So G is equal to S+3. Berapa? S plus 25. Okay. Then both G. Okay, there you go. Can you see? Okay. Wahidah? Wahidah,
Yes, Doctor.
what is the value of the corner frequency?
Is it we scan at the maximum point? Which is the frequency is 4.93 radian per second with the magnitude of negative 90.4 dB.
Maximum berapa?
The frequency
Minus 19.1. Maximum. $4.87. 4.87. Betul? So what is the zeta value? Hadif. What is the zeta value? Hadif, datang.
Ya, Doktor.
Zeta value.
Tak pasti, Doktor.
Tengok sini. Tu. Betul?
Zeta value 5.
2. 5? Kok biar betul? 2 zeta omega n. Dua darab 0.2.
0.2.
0.2. Okay, 0.2.
0.2.
Okay, 0.2. So that is the plot for the MATLAB here. So if you want to plot using freehand draw, okay. So this is plot using a freehand draw. There, 0.2. Ada tulis kat situ, kau tak baca kot. Normalize first, okay. So you normalize the transfer function and then you plot one by one. How many factors? You have a k, you have a 0, you have a poles, and you have a complex conjugate poles. 1, 2, 3, 4 factor. Okay. And you plot one, and then you add all together. Okay, and then you will get the plot, which is here. This is what we call as the open loop book plot. So what info we can get, information that we can get from the open loop book plot. Okay, so we go to the characteristics. Okay, using your mouse and go to the peak response. That is your peak response. Okay, and then goes to the minimum stability margin. And then goes to the all stability margins. Ada? Tak ada. Dia tak tunjukkan. So dia just tunjukkan the peak frequency, okay, and the magnitude, which is the minus 19.2. So this is what it calls as open loop boat plot. There is another one, we call it as a closed loop open boat plot. So for closed loop, you just apply a feedback lah. So let's say T is the closed loop, so it's equal to G divided by 1 plus G. So you get the closed loop, okay? And then both T. So both plot have two, one is open loop, one is closed loop. So for closed loop, I share with you the plot. So this is the plot for closed loop, okay? It's about the same, but different value, different info we can get from the plot here, okay? And all stability margins, okay? So that is for your information. We have two type of boat plot. One is open loop, the other one is the closed loop. So I will explain later what information we can get from both plot open loop and both plot closed loop. Stability. So that will bring you to the stability via both plot. So if you're given both plot, how do you know that the system is stable or not stable? So stability for a closed loop system can be determined using open loop system. Okay, both plot open loop system. A closed system is stable if the magnitude of the open loop system is less than 0 dB, which is unity gain at the frequency where the phase is plus minus 180 degrees. Example 3. Sketch the both plot and use the MATLAB to get the actual plotting. Determine the range of K which the unity feedback system is stable. Let GS is equal to K, S plus 2, S plus 5, S plus 4. Okay. So for convenient, use K equal to 40. So this is the gain. When we have open loop poles at -2, -4, and -5. Okay. So we plot lah. Okay. So 40, S plus 2, S plus 4, S plus 5. So G is equal to 40 divided by S plus 2, S plus 4, yeah, other class. S plus 2, S plus 4, S plus 5. Okay. And then boot. Okay. Right. So this is the plot. Can you see? Can you see the plot, guys? Okay. Then call a grid. Okay. And then go for the characteristic. All stability margins. Right hand click. Okay. So you can see that from there, it will give you this one, gain margin, which is 19.5. How do I get 19.5? 0 minus 19.5. So this 19.5 is at the frequency 6.16. So 6.16 at the phase response, 6.16. Okay, it's about here. Okay. 6.16 is where the phase curve cut at minus 180 degrees. So when the phase curve cut at minus 180 degrees, meaning that it will give you gain margin. Okay, it will give you a gain margin. So I copy this one and I share with all of you. Okay. Right, so this one. So this one we call the 6.16 radian per second. We call it as a omega phase crossover phase crossover frequency, omega CP. Okay. Omega phase crossover frequency. So that is the gain margin. So the gain margin at K with 40 at phase minus 180 degrees, omega GM, which is 7 radian per second, which will give you magnitude of minus 20 dB. So far the gain margin is 20 decibels. The one that we get here is about 19.5. So more or less is okay. Okay, so gain margin 19.5 decibel or 20 decibel. Okay, it's positive. So the system is stable at K equal to 40. But if gain margin is negative value, so this one will cause you unstable system. Okay, so as long as the gain margin is positive, so the system is stable. Therefore, an increase of gain of 20 decibels or 20 log 10 is possible for stability before the system become critical or marginal stables. Hence, the gain for stability is 400, which is 40 multiplied by 10. So the range is between 0 to K to 400. System will become critical when gain is equal to 400. Let's say we change the gain just now. Okay, change to 400. Okay, just now is 40 kan, so we change to 400. Okay. Then we both G. Okay. But okay, put the grid and find the stability, all stability margins. So you can see here, okay, you can see here, the frequency is 6.32, okay, and it will give you the gain margin is almost 0, okay, gain margin 0, phase margin also 0, so considered as marginal stable, okay, where the frequency almost the same, 6.32 and 6.16. Actually, we can retry again these simulations so that the frequency of the omega GM and omega PM is the same. Okay, we can vary the K value until we get the marginal stable, and I will discuss it in the next class. So if you go to the lecture, I'm not sure whether the our lecture room is ready or not. Have you gone to this morning class? Have you attended the face-to-face class this morning, guys? Is it the classroom is ready or not? Hello? Is it the classroom is ready or not? Hello?
Not sure, Doctor, because the face-to-face class for our section is begin for this evening class.
Evening class, okay. So I gave 1 week first. I try to check the classroom because it's already 2 years left without maintenance, without cleaning. So I have to make sure the room is clean, the projector is good conditions, and the whiteboard is clean and everything is clean, so that I can call for a face-to-face class. So at the moment, we still maintain online. I will inform you on day before Wednesday whether the class is ready or not. Okay. Can you wait for my signals, guys?
Sure,
Yes,
Doctor.
Okay. Because 2 years left, I don't know the maintenance of the class. Is it okay or not? Is it dirty or clean? I'm not sure about it. Okay, so thank you very much for your attention, and I will see you on Wednesday. Nuratika? Ya?
Yes, Prof. Ya.
Berhenti kat mana? Berhenti kat mana? Wakaf?
43, page 43.
Ingatkan saya. Thank you very much. Bye-bye.